Okay, so in this example problem, we're going to be examining the barometric pressure equation, which basically describes the change in pressure in the atmosphere as a function of T and Z. So to look at that equation, we're going to examine an example problem where we have a car at a level Z naught, where the pressure is P naught, the density is rho naught, and the temperature is T naught. And we're going to watch that car travel all the way up to some level Z, some arbitrary level Z, where the pressure is P, the density is rho, and the temperature is T. Now, this level Z naught is not necessarily sea level. It's just some reference level that we've arbitrarily designated as Z naught. So to begin, our assumptions are: one, we have a static ideal air, so we can use the ideal gas law. We have gravity is the only body force, so we have no magnetic fields, no electric fields of relevance here. Three, temperature in the atmosphere between Z naught and Z, so the temperature in the atmosphere between these two levels varies linearly. And four, we have a constant gravitational field between these two levels. So there is a significant enough elevation difference here for the density to vary in the air, but not the gravitational field of Earth in this case. We're going to examine this on Earth. Our objective here is to find the percent difference in air density between Z naught and Z. And a reason you might care about this is, for example, if you have an internal combustion engine, the density of the air is going to be an argument to both the efficiency of your combustion process and to your drag calculation on the vehicle. So there's going to be a balance there to determine what the overall power efficiency of the vehicle will be as a function of elevation. So we're going to note that, again, Z naught is an arbitrary reference level that is not necessarily sea level. So our knowns here are Z naught, we're just going to take as 0. The temperature at Z naught is 30 degrees Celsius. The pressure is 101,325 pascals, so approximately 1 atmosphere. And we're not sure what the density is. At the level 1, so this level right here, so we should designate that as 1, 1, 1, and 1. The pressure is unknown. The temperature is 25 degrees Celsius. The elevation is 1,000 meters, so a kilometer, and the density is also unknown. So, going to the next slide here, we're going to see that we really need to find a way to express the pressure as a function of the density and the temperature. So we have an equation of state here for an ideal gas, which is the ideal gas law, which describes that the product of the pressure and the volume is equal to the product of the number of moles, the universal gas constant, and the temperature of the gas. So here we have R as our universal gas constant in units of joules per mole Kelvin, and it's approximately equal to 8.3145. Now what ends up happening is we're going to derive a special form of the ideal gas law where we start with it in its standard form, and we divide by V on both sides, so we have P equals N over V times RT. Now this term right here, N over V, this is just the number of moles per cubic meter of gas. So if we multiply by the molar mass of air divided by the molar mass of air on this side of the equation, which is just equivalent to multiplying by 1, noting that the molar mass of air is in units of kilograms per mole, then what we can do is play a little game here where we take the molar mass of air and multiply it by N, and then keep the 1 over molar mass of air as a constant factor out here. So the molar mass of air times N, it's kilograms per mole times moles. So this is just a unit of kilogram. This is the mass of the air. So you can see here that we just have the mass of the air divided by the volume. Well, the mass of the air divided by the volume of the air is the density of the air, where again, we're noting that the mass of the air, this term right here, is in units of kilograms. We still have this 1 over molar mass of air term out here, which we needed from the original constant factor up here. So this is just kind of hanging out on the outside of this right-hand side. But now we have the density of the air times R times T, where again, R is the universal gas constant. So when you have the universal gas constant and you divide it by the molar mass of the air, you get the specific gas constant of air. So the universal gas constant divided by the molar mass is the specific gas constant. In this case, we're talking about air, so we're looking at the specific gas constant of air. And the specific gas constant of air has units of joules per kilograms Kelvin, which is opposed to the universal gas constant, which has units of joules per mole Kelvin. And this is a very important distinction. So now we have an equation P is equal to rho R hat T, right? So from now on, we're just going to call rho air rho and R hat air R hat, just for brevity. So now we have an equation P equals rho R hat T, where R hat is our specific gas constant, and we have an equation of state for the pressure, which describes it as a function of rho and T. Okay? So on this next slide here, we can say, okay, well, what if we apply this new equation to both Z naught and Z1? So this should be Z1, P1, rho 1, T1. So what if we take this equation of state and we apply it to our different levels? Well, we know what P naught is. That's just 1 atmosphere. We know what T naught is. That's just 30 degrees Celsius. So we could use this equation to calculate rho naught. However, we don't know what P1 is, and so we can't use this equation to calculate rho 1. So we need to calculate P1 to evaluate rho 1. So our initial instinct is, well, this is a static fluid, so we can use a form of the hydrostatic pressure equation. So moving on to the next slide here, if we look at our diagram again, we could see that, we're starting at P0, T0, Z0 and going to P1, T1, Z1, where Z is positive up and G is opposite but parallel. And if we were to apply the standard simplified hydrostatic pressure equation to this setup right here, then it would look something like P0 is equal to P1 plus rho G times the difference in Z's. Now, the problem with this equation is it assumes an incompressible, isothermal, and constant G. So incompressible gas, isothermal system, and a constant gravitational field. In other words, this equation assumes that we have a constant density and a constant gravitational field. Now, we do have a constant gravitational field, so that's great, but we don't have a constant density because the system is neither incompressible, so in other words, the density is a function of temperature and pressure, so the density is changing in this problem depending on where you are in Z, and we don't have an isothermal system because T0 is not equal to T1. So we can't use this simplified form of the hydrostatic pressure equation. We have to do something a little bit more sophisticated. So if we go back up in the derivation one level, then we can use the unsimplified form of the hydrostatic pressure equation before we make these assumptions of incompressible and isothermal. And that unsimplified form is just dP dz, the full derivative dP dz, is equal to negative rho g. So essentially, we're just going to be using this ancestor equation right here. Now, if you make the assumption that rho is constant and g is constant, you can take this equation and derive this equation. So here's that unsimplified form, that ancestor equation again. And if what we end up doing is we plug in our equation of state here for our density, so we know what our density is from the last ideal gas law that we derived. dP dz is equal to negative p over r hat t times g. And this is just the ideal gas law we just derived plugged in for rho. So we just separate variables. So we have 1 over p dp is equal to negative g over r hat t dz. So here we can realize that on the left-hand side, we are good to integrate. Our variable of integration is p, and we have a function of just p. Here on this right-hand side, our variable of integration is z, but we have t, which is another independent variable. So we need to find a way to express t as either a function of z, so we can integrate it on the right-hand side, or a function of p, so we can integrate it on the left-hand side. T as a function of z is a relatively intuitive and convenient conceptualization if you use the concept of the temperature lapse rate, which we'll review in this next slide right here. So T as a function of z. If we end up assuming, again, as we have, that the temperature varies linearly between z0 and z, then we can assume that the form T equals T of z looks like T equals T0 plus mz, where T0 is our temperature at the reference level, T is our temperature at some arbitrary z, m is a constant slope, a constant linear slope, and z is just the distance from z0 to z, right? Some distance h, essentially. So if we assume that the temperature varies linearly between our 2 points, then our temperature could be described by this equation right here, where m is essentially the slope of the line. So m here is our temperature lapse rate. It has units of kelvins per meter, and this is a common conceptualization in atmospheric problems where somebody might say, in this layer of the atmosphere, I'm going to assume that my temperature varies linearly or quadratically or logarithmically or whatever they're going to assume. Here, we're going to assume that our temperature varies linearly by assumption 3, and so our temperature lapse rate is just some constant value. It's the slope of that line, and it has units of kelvins per meter. So our T equals T of z is equal to T0 plus mz. So we're going to assume that T is equal to this equation right here, this linear offset right here between the two temperatures at the two different elevations. So now all we have to do is plug in our new temperature lapse rate equation, T equals T0 plus mz, into our separated variables equation. And again, this separated variables equation comes from the ancestor form, so to speak, the unsimplified form of the hydrostatic pressure equation with the ideal gas law plugged into it, with the equation of state for the gas plugged into it. And again, this temperature lapse rate equation is from our assumption number 3, that temperature varies linearly in our problem. So the 1 over p dp, the left-hand side, stays the same. The right-hand side now becomes negative g over the quantity r hat times the quantity T0 plus mz times dz. So this left-hand side is with respect to p, and this right-hand side is with respect to z. So now we integrate both sides of the equation, and we're going to integrate from state 0 to state 1 on both sides of the equation. This is a thermodynamic concept where you can integrate from one state to another. I'm not going to elaborate much further on that right now, but it is a common practice in thermodynamics, and we're going to utilize it here. So we're integrating from state 0 to state 1 on both sides of the equation, and then you basically just say, what is my pressure or rather, let's go up here. What is my pressure at state 0? Well, my pressure at state 0 is P naught. What is my pressure at state 1? Well, my pressure at state 1 is P, just some arbitrary P. And that's how you map state 0 to state 1 to this integral down here. And then in a similar fashion, you say, okay, what is my Z at state 0? Well, it's just Z naught. What is my Z at state 1? Well, it's just some arbitrary Z. So I'm just going to write Z up there. So that's how you map this integral on the right-hand side to this integral right here. And you will see in some texts that to differentiate the upper limit of integration from the variable of integration, they will add some kind of symbol to the upper limit of integration, like they'll call it P tilde or something. We won't do that here, but you may see that. So now it's just a simple matter of actually integrating these two sides of the equation. So then taking this equation from the last slide and performing the integrals on the left-hand side and the right-hand side, this left-hand side integral is not too difficult. It's just the integral from P naught to P of 1 over P dP. You are just getting rid of some absolute values using a log rule. So the difference of two logs is a log of the quotient. So that's where this natural log of P over P naught comes from. P and P naught are both positive. Get rid of the absolute value, and that's where natural log of P over P naught comes from. This is the left-hand side integral. Now the right-hand side integral, the integral from z naught to z of 1 over t naught plus mz dz, this is a little bit more involved. We use u substitution here. And there's one thing I do want to note about this before we move on. So again, we're just doing our standard u substitution here. We're just letting u equal t naught plus mz. We're finding du dz, etc. So I won't go over the u substitution too much. But one thing I do want to say is, with this u substitution, since we're doing a definite integral, we also need to change our limits of integration to be in u space instead of z space. So we see here that our limits of integration start off at z naught and z. So we integrate from z naught to z. But when we go to u space, as we are right here in u space, we say that, well, if u is equal to t naught plus mz, at z naught, u is equal to t naught plus mz naught. And that's why this z naught becomes t naught plus mz naught. And at z, u becomes t naught plus mz, and that's why this z becomes t naught plus mz. So you need to change your limits of integration from z space to u space when you do u substitution. And that's why we change the limits of integration like we do right here, from z naught to z to t naught plus mz naught to t naught plus mz. And again, with that in mind, we're just performing this integral, and we do get 1 over m, so the temperature lapse rate m, which is defined as negative. So 1 over m times the natural log of the quantity t naught plus mz over t naught plus mz naught. And adding in that constant factor that we didn't include in the integral, negative g over r hat, which is applied right here, times this integral, which we just found is this value right here, we get that the right-hand side is equal to negative g over m r hat times the natural log of t naught plus mz over t naught plus mz naught. So this is the right-hand side of this equation right here, and this is the left-hand side of this equation right here. So now we're pretty much done and ready to solve for the pressure. So this is just the equation from the last slide, and we're ready to exponentiate both sides to solve for the pressure. But before we exponentiate, we're going to use one more log rule, which is some constant factor times the log of a quantity is just equal to the log of the quantity to the power of that factor. So we're going to use that before we exponentiate. So the natural log of p over p naught is equal to the natural log of this quantity right here to the power of negative g over m r hat. So this is just a log rule that we're applying. Now we have pure logs, so to speak, on both sides. We can exponentiate, and that gives us p over p naught is equal to the quantity t naught plus mz over t naught plus mz naught to the power of negative g over m r hat. Now, if we say that our z naught is equal to 0, which is not necessarily sea level, again, but if we say that our z naught is equal to 0, which it is, then this part of the term in the denominator goes away, and we get t naught plus mz over t naught. Well, t naught plus mz is just defined as t, so this right-hand side just becomes t over t naught to the power of negative g over m r hat. So here we have our final form of the equation that we're going to use, which is just solving for p. P is equal to p naught times the quantity t over t naught to the power of negative g over the quantity m r hat. So this is the final form of our barometric pressure equation that we're going to use to solve this problem. This is a very useful equation and applies specifically for the assumptions that we outlined on the first page. Okay, so now that we have this equation established, we rewrite out our knowns, and we can first, before we start plugging in numbers to this more general equation, we need to determine what m is. Well, again, we know that t is equal to t naught plus mz. In this form, assuming that our temperature is decreasing, m has to be negative. So we determine our temperature lapse rate as just the difference in temperatures over the difference in elevation, and we find that our temperature lapse rate, our linear constant temperature lapse rate, is negative 0.005 kelvins per meter. So that's what m is equal to. So it is negative as it has to be, as required by this form of t. So now we're ready to plug in values to our barometric pressure equation, which is this equation right here. So our pressure at our arbitrary level Z, in this case 1,000 meters, is equal to the pressure at the reference level, P naught, which is 101,325 Pascal, times the quantity of T over T naught. Well, the temperature at Z, in this case, is 25 C. So we have 25 plus 273.15 Kelvin, because again, all temperatures, when you use the ideal gas law, have to be expressed as absolute temperatures or temperatures in Kelvin. You cannot use temperatures in Celsius with the ideal gas law. So here we have our temperature T, or our temperature at our arbitrary Z, is 25 degrees Celsius. And so we have 25 plus 273.15 Kelvin. And then we divide that by T naught, or our temperature at our reference level, which is again 30 degrees Celsius. So 30 plus 273.15 Kelvin. And then we're putting that to the power of negative G over M R hat. Well, we have our negative here. Our G is, we're assuming we're on Earth, so 9.81 meters per second squared. Our M, we just calculated, has to be negative according to the form of the temperature lapse rate equation that we use. So M is negative 0.005 kelvins per meter. And our specific gas constant of air, which is again in units of joules per kilogram Kelvin, is for air 287.1 joules per kilogram Kelvin. Now, if you plug this into your calculator, you'll see that your pressure at your elevation 1,000 meters, adherent to the assumptions on page 1, is equal to 90,439.3 Pascal. So again, 90,439.3 Pascal is the pressure P1. So now we can finally fill in this chart, and we see that our pressure here is 90,439.3 Pascal. So as expected, as you go higher and higher up in the atmosphere, as you elevate in the atmosphere, your pressure decreases. So as you go from 0 meters to 1,000 meters, as you go from 30 degrees Celsius to 25 degrees Celsius, your pressure decreases. It goes from 101,325 Pascal to 90,439.3 Pascal. So that is a significant reduction in pressure. So now with this table filled out, we can finally use the ideal gas law to calculate rho naught and rho 1 and find our reduction in density. So again, here's our table. The only unknowns are rho naught and rho 1, and we're going to use the modified form of the ideal gas law using the specific gas constant to calculate these two densities. So here we see that we have P naught is equal to rho naught R hat T naught, and we just solve for rho naught. So that's what this expression is right here. Plugging in P naught, 101,325 Pascal. R hat, again, is the specific gas constant, 287.1 joules per kilogram Kelvin for air. And our temperature at the reference level Z naught is 30. So 30 degrees Celsius expressed as Kelvin. We get that our density at our reference level is 1.1642 kilograms per cubic meter. And then again, we applied the modified form of the ideal gas law for our arbitrary level Z, in this case 1,000 meters. Rho 1 is equal to P1 over R hat T1. P1 is the pressure we just saw for, 90,439.3 Pascal. R hat, again, is the specific gas constant of air, 287.1 joules per kilogram Kelvin. And T1 is the temperature at that arbitrary level Z, 1,000 meters, 25 degrees Celsius, expressed in Kelvin. So that density solved for is 1.0565 kilograms per cubic meter. Now, if we find the percent difference between the density at 1 and the density at 0, so to speak, and we use this equation to do so, the percent difference equation, we see that our percent reduction in density is 9.25%. So our density at our level 1 is 9.25% lower than our density at 0. So we have experienced a 9.25% reduction in density, going from 0 meters at 30 degrees Celsius to 1,000 meters at 25 degrees Celsius. So this would be the starting point for an analysis to determine what is the change in efficiency of my thermodynamic cycle when the density goes from this level to this level. And then how does that balance off with the efficiency in my drag characteristics of my vehicle as my density goes from this level to this level? And you have to perform those thermodynamic and fluid dynamic analyses, balance them out, and then find out what the aggregate result is to determine how the overall power efficiency of your vehicle changes with elevation. That is a completely separate topic that will be for another video perhaps, but this is where we'll stop for now. This is the first part of that analysis. Gets you a long way, so this should be good for the time being. Thank you very much for watching. I really appreciate it, and I will see you next time.